Today we are going to start the even reaction. So even is called unimolecular elimination reaction. So we can use a tertiary alkyl halide and here we will use a base. Now look at here. The halogen containing carbon is called alpha and alpha neighboring carbon is called beta. So beta 1, beta 2 and beta 3. So they are all equal. So beta 1 equal to beta 2 equal to beta 3. So we have alkene as a product plus H3O plus Br minus. Let me tell you the mechanism. So even have same mechanism like SN1, especially formation of intermediate. So if you look at this alkyl halide, carbon bromine bond is polar in nature because of difference in electronegativity between bromine and carbon. Bromine is more electronegative, carbon is less. So it would break towards bromine. And here we have a carbocation, and this is reversible step because this is not a good leaving group. So we have this carbocation. This is the reaction intermediate. This carbocation we have, and Br minus is my leaving group. So we can expand the any beta hydrogen, either beta 1, beta 2 or beta 3. Any beta hydrogen we can expand. Suppose we are going to expand the bottom one. This one, 3H like this. So now H2O is here as a base. This H2O is acting as a base here. So base property is to grab the hydrogen, the proton. Which proton? Beta proton. This is alpha was and this one is beta. So base is going to grab any of the beta hydrogen and it would donate the electron to this bond. So overall you have alkene. So CH3, C, CH3, double bond CH2. So this would be my alkene. So in the mechanism, we can see the first step is a formation of carbocation. In the second step, base grabs the beta hydrogen. So it is basically the elimination of alpha halogen and beta hydrogen. So it is the elimination of alpha halogen and beta hydrogen. Clear? Please tell me it makes sense. For example, suppose we have this one. And we have to write down the product directly. So this is my alpha carbon. Alpha neighboring is called beta. So this is beta 1. This beta 2 and this beta 2 is identical in nature. So we can say beta 2, beta 2. I said that it is an elimination of alpha halogen and beta hydrogen. It means we can fix a double bond between alpha and beta. The double bond would be between alpha and beta. So we have two different kind of beta. So we have two different alkene. So first alkene would be between either alpha and beta 1 or alpha and beta 2. Suppose we are going to remove the bromine and a hydrogen of beta 2. Any of the beta, right or left. So it would be a double bond between alpha and beta 2 and this beta 1 carbon would remain same. Alpha, beta 2. There is another possibility. If we can eliminate the beta 1 hydrogen, the top one, so the double bond would be between alpha and beta 1, like this, alpha, beta 1. Make sense? Please tell me, everyone. I will discuss later which one is more stable out of them. But right now, I am just going to tell you how many product we can generate. Clear? Okay. Now the key point is we are talking about E1. So it is unimolecular elimination, unimolecular reaction. The second thing, first order kinetic. Third thing, rate directly proportional to the concentration of alkyl halide. Whenever order of reaction is first order, then it depends only on the concentration of alkyl halide. Base forms the elimination product by removing a proton from beta carbon. So the rate directly proportional to stability of carbocation. So if you are going to compare the rate of E1 reaction, I said rate of E1, then it would directly proportional to the stability of carbocation. So more stable the carbocation, faster the rate of E1. Clear? I have a question for you. Suppose this is a carbon having one bromine, this side ethyl, this side methyl, this side isopropyl. And we are going to react with the base, suppose H2O. Then tell me how many alkene we can get. How many products? Number of product. Tell me. I already told you the number of alkene depend on number of beta H. If you have 3 different beta, then 3 different alkene. If you have 2 different beta positions, then 2 different alkene. If single, then only one alkene. Please tell me. Yes, this is my alpha carbon. This is the beta 1, which is CH2. This is the beta 2, which is CH3. And this is just a CH, which is beta 3. So we have 3 different beta. Now how we can generate the product? So first you can keep double bond between alpha and beta 1. So rest of the group would remain same in this way. So this is the first product. Second, we can keep the double bond between alpha and beta 2. You can see this is alpha, this is beta 2. This one is alpha, this one is a beta 1. And the third, we can keep a double bond between alpha and beta 3. So we have 3 different alkene. Make sense? Please tell me. Perfect. Now we can say here 3-degree alkyl. 3-degree alkyl halide gives only E1, only E1. And if you have 1-degree and 2-degree alkyl halide, only E2. And the rate of leaving group would be again iodine is the best, then bromine, then chlorine, then fluorine. Because iodine is the best leaving group. Now we are going to talk about the stability of alkene. Because once you have more than one product as alkene, then we have to compare which one is a more stable alkene, which one is a less stable alkene, like that. So we should know how, like, which one is a major alkene, which one is a minor alkene, and that depend on the stability of alkene. So next is stability of alkene. Now look at the trick here. Whenever you have alkene, then keep a circle around the double bond carbon. Always keep a circle around double bond carbon. The carbon bonded to the circle is called alpha carbon. And the hydrogen of alpha carbon would be considered as alpha H. So here we have 3, here we have 6, here we have 9, and here we have 12. So more the alpha H, more would be the stability. So fourth would be the most, then third, then second, then first. Make sense? Snigdha?
Yes, it makes sense.
Perfect. Suppose we have a bond line alkene like this. Now tell me how many alpha H in 1, 2, and 3. So how many alpha H in the first one? Let's do one by one. How many alpha H in the first one? So you can keep a circle. Neighboring carbon is called alpha carbon. Alpha, alpha, alpha. How many alpha H? 3, 3, 6, 3, 9.
9.
Okay, now in the second one, how much?
3, 4, 5, 6, 7, 8, 9, 10.
I think yes. Alpha, 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 alpha. So 3 to 5, 3, 8 to 10.
Mhm.
What about the third one?
3, 4, 5.
Very good. So more the alpha H, more would be stability. So second, then first, then third. Clear?
Yes.
Perfect. Now one thing, note point. More stable alkene would be called as JetSav or SETJAF. Less stable alkene is known as half-man alkene. Half-man alkene. So let's do this one. This one. If you look at this, problem, this one, we have two different alkene as a product. Now we have to figure out which one is a major, which one is a minor, which one is a SETJAF, which one is a half-man. So I told you the formula. So keep a circle around the double bond and then find out the alpha H. How many alpha H here?
1, 2,
Alpha,
3,
alpha,
4,
alpha.
5, 6, 7.
3 to 5 to 7. And how many alpha H over here?
4.
So more alpha H, more stable. So this is more stable. So
Okay.
more stable means SETJAF or
Mhm.
JetSav. And less stable means half man. Clear?
Yes.
Any doubt?
No.
In general, SIDJAF is a major alkene. 90% cases, SIDJAF is a major alkene. But in some cases, half man can also be major. But I will tell you at which condition we will say like half man is the major one. Okay.
Okay.
What about this one? Tell me here, how many alpha H in the first one here?
3, 6, 9, 10, 11.
Yes, 11. And how many alpha H here?
1, 2, 3, 3.
2 and 1 here. Very good.
Yeah.
This is the circle. So this is the alpha carbon. This one is alpha. So 2 and 1, 3.
Mm-hmm.
And how much here?
3,
7.
4, 5, 6, 7.
Yes. So SIDJAF is this one. This one is a major one. Okay.
Yes.
Any doubt about E1?
No.
So the key point about E1 is what? Carbocation is an intermediate. Okay. Next E2. Two means bimolecular. So this is a bimolecular reaction. Okay, we can first discuss with this example. Suppose here we have a carbon chain. Okay, like this. Clear? And here we are using a base. So this is a concerted type mechanism. This is alpha, this is beta. So it would grab the beta hydrogen first. Beta hydrogen would donate the electron to this bond and then X would leave. Clear? There is no carbocation. Clear?
Yes, because
So
it's
we have
just
a
a
double
one
bond
step,
here.
right?
This would be my alkene. This would be the H with base. And here X minus as a leaving group. Clear?
Yes.
So if we are going to write down the key point for this reaction, then we can say bimolecular, second order kinetic, which means rate directly proportional to the concentration of alkyl halide as well as base. Clear? Make sense?
Yes.
And we have done already the stability of alkene. So now one thing I would like to tell you here, at which condition the half man or SIDJAF would be the major one, okay? And that is called regioselectivity. This is called regioselectivity. So regioselectivity is like, suppose you have this alkyl halide and here we have a base. Now you know that how many different beta, let's figure out. So this is my alpha, this beta 1 and this beta 1 is exactly same, but this beta 2 is different. Make sense?
Yes.
So how many alkene we have?
2.
So 2 alkene, that would be this one. So first we will keep a double bond between alpha and beta 2. The second double bond between alpha and beta 1. Any beta 1, either left or top. Suppose this one. Clear? It makes sense?
Mhm.
So the important thing is whenever you have two different alkene and they are not stereoisomer, they are structural isomer. They are structural because they have different name. Clear? If you are going to name this compound, then what would be the name? 1, 2, 3, 4. So that would be considered as 2-methyl butene. And this one is what? 1, 2, 3, 4. This is 2-methyl butene. So they are not stereoisomer, they are structural isomer. So whenever you have two different products in terms of structural isomeric, then that is called regio one, and out of them, this one is a major one. Why? Because ZJAF is a major one, most stable. Am I right?
Yes.
So that means it is a regio selective. Clear?
Yes.
This is called regio selective because ZJAF is major here. This is called ZJAF alkene or ZSAF, and this is called Halfman. Make sense? Any doubt?
Yes.
Now the note
So
point. Mhm.
I actually do have a question.
Yeah.
So, like, okay, I don't know if I'm confused with this, but why is it that that one is the first one is more stable? Wouldn't we pick the one that has like, when you're naming something, like with less numbers, if that makes sense? Or does that not play into the factor of it being
First of all,
stable?
naming is related to the name of compound. There is no mean to relate with the stability.
Okay.
Stability
So
is
is it
always determined by the alpha H of alkene. So if you look at the first one, this one, how many alpha H
uh,
around the double bond? 3,
um
6,
three,
and 9.
6, 9? Mm-hmm.
While the second one just 3 and 2, 5 alpha H. So less
Okay, that
stable,
makes
this
sense.
one, less stable is called half-man alkene. This is my half-man. And the most stable is this one. This is called Jatsav or Sedjab. Clear?
Got it. Yes, makes sense.
Here in this case, Sedjab or Jatsav is my major one. I'm
Mm-hmm.
going to tell you at which condition we can say half-man can be major. So note point is whenever we are going to use bulky base, bulky base. Bulky base is like this one, tertiary butoxide, and this one. They both are bulky in nature. So whenever you have a base is bulky, it means half man would be the major one. Half man would be more than ZJAF or ZSAF. Clear? For example, suppose we have this alkyl halide and we are going to use this base. So you know that we have two products. One is this one and one is this one. Make sense? And you know that this is my half man and this is my ZJAF. Clear? Because base is bulky, because base is my bulky, so we will say this half man would be the major here and this would be the minor. Make sense?
Yes.
And if you are going to use a light base, suppose methoxide one or NaOET one, NaOET. So again we have two product, but this time ZJAF would be the major one. Clear? So this one would be the major one and this one would be the minor. Make sense?
Yes.
So these are some bulky base like tertiary butoxide. This one, there is some name like DBU and DBN. There is no need to know the full name of these two. It will always be in this name in the reaction, okay, dBu and dBn. So this one is also considered as bulky. Clear? Now the second condition, when leaving group is fluorine, if you have a fluorine as a leaving group, and you can use any base like bulky or any base, suppose small base as well, suppose this base, then again half man would be the major one. Again half man would be the major one. So this is my half man, this is my Sedjab, so it would be the major one. It makes sense. So always memorize these two conditions, when base is bulky or when leaving group is fluorine. Clear?
Okay, so if a leaving group is a halogen,
Not halogen,
halogen or
fluorine only.
only fluorine?
Yes,
Fluorine and bulky,
yes,
Hoffman is major, but if it's not,
yes.
then it's ITF is major.
And how can you correlate these information? Look at the spelling of half man. So you can see here F is coming. So F means fluorine, you can correlate as a leaving group. Clear? And second thing you can correlate, half man means a man which is half in part. So half man is always an unstable thing. So you should say unstable would be the major here. Make sense?
Got it.
Yeah. So do not memorize, just try to, correlate the information.
Got it.
So now the next is stereoselective of E2. Stereoselectivity. Stereoselectivity of E2. First thing we have learned regioselectivity. Regio means we have two different product. Out of them, which one is major, which one is minor, like Sedjaf and Halfman. But in stereoselective, we have a product and they are stereoisomer of each other, like cis and transform. And then we can say out of them which one is more stable. Generally, trans or E form is more stable. So we can say that would be stereoselective. Clear? In this way. This is my alpha, and now you can see both the beta is same. Clear? Make sense?
Yes.
So you can draw the double bond either this side or left hand side, both are same thing. So suppose this is my alkene. Clear? It makes sense.
Yes.
Now this alkene is in the trans form or E form. You can see groups are empty.
Mm-hmm.
And it can form another isomer that would be called as Z, like this. You can see this is Z. Make sense?
Yes.
So whenever we have two stereo product, you can see there is stereo isomer E and Z. And out of them, trans is more stable than cis. Trans is more stable than cis, or E is more stable than G. So we can say this is stereo selective. Clear? So this is stereo
Yes.
selective reaction. Any doubt?
No.
So we can say generally whenever two beta positions are same, then it can generate two stereoisomer. Out of them, trans is a major one. Clear?
Yes.
The next thing is stereo specific. Stereo specific of E2. Now look at here. Generally, E2 reaction is anti-periplanar. This is called anti-periplanar. Do you know what does it mean? Anti-periplanar means leaving group and beta hydrogen should be anti, should be opposite, should be anti. And yes, it is anti here. Bromine is, you can see in the up, this is the, sorry, I made mistake here. I think this is H, this is H here. Give me 1 second.
Okay.
So you can see this is my alpha and this one is my beta. Clear?
Mm-hmm.
So you can see the position here. Bromine is up and hydrogen is, opposite end. So this is anti-periplanar. And suppose here we have a base NaOET. So base is going to grab this hydrogen. It would donate the electron to this bond and Br leave. Clear?
Mm-hmm.
So what should be my product? Look at the carbon, alpha and beta. There should be a double bond. Alpha carbon, beta carbon. Now look at the group. pH with the wedge and here hydrogen on the wedge. Wedge means same side. Suppose this is my pH. So this side we have hydrogen. And this is the das methyl and this is the tertiary, alkyl group. So they should be in the same side. So Me and then this one. Clear?
Okay.
So this is
So
called
everything on the
stereoisotopic.
wedge is on it goes to the same side, right?
Yeah. If it is not in the NT, then you have to rotate the beta position to keep it NT, means opposite to the bromine.
Okay.
Yeah. That is called rotation technique. It makes sense.
Mm-hmm.
Now look at this one. And one more thing, you sometimes you can draw this wedge and dash into the Newman projection. If you are looking from this angle, now look at hydrogen is vertically down, so keep hydrogen is vertically down.
Mm-hmm.
Now wedge is right side, so wedge is right, so pH, and the dash is in the left, so dash is my methyl. Clear? So this is my
Yes.
front carbon. Now look at the rear carbon, rear one. Bromine is on the plane bond, which is up, so bromine is up, and then hydrogen on the wedge, so hydrogen should be right, and this group, tertiary alkyl group, is in the dash, so left, like this. Clear?
Mm-hmm. So whenever you're drawing the Newman projection for the one on the back, it kind of flips, right? Like the H and the alkyl group, like they kind of flipped positions, right?
Yeah, means
Okay.
it's depend on the angle of observation. If you are going to observe from this angle, then the wedge would be right, dash would be left, and the plane bond would be either up and down. So this is down, so keep it down.
Okay.
So I said it is anti-periplanar. So bromine and this hydrogen is anti to each other. So you can easily remove them. And there is a double bond between this alpha and beta position. So you can see methyl is anti to the hydrogen. Methyl is
Mhm.
anti to the hydrogen.
Yep.
And now tertiary alkyl group is anti to the pH. Tertiary alkyl group anti to the pH. Clear?
Yes.
Makes sense?
Makes sense.
Write down. Okay, no need to write down this. I will share this file with you. Okay.
Okay.
Suppose this one, we have this case, suppose. Now in this case, you can see here, the group is not in anti direction. Can you see? The hydrogen, this is my alpha, this is my beta 1, beta 2, but beta 2 have no hydrogen. So there is no mean to remove a hydrogen from beta 2. So you have only one position, beta 1. Clear? Makes sense?
Because it's tertiary, right? That's
Yeah,
why.
this is tertiary, so there is no hydrogen here. So here, if wedge is my chlorine, it means a dash would be hydrogen. Clear?
Yes.
So let me draw the Newman of it. So I can see if you are looking from this angle, so you can see this plane bond is up, so keep up like this. Wedge is my chlorine, so wedge in the right. Dash is hydrogen, so dash in the left. Clear?
Mm-hmm.
Now look at this one. Here, this is my plane bond, which is ethyl group, so ethyl is down. And now wedge is my hydrogen which is in the right. And now methyl is on the dash, so left. Clear?
Got it.
So now look at the red one. Suppose this is the front carbon, chlorine in the right hand and this angle. So I would like to keep the hydrogen, this hydrogen, the green hydrogen should be anti to the chlorine. So you can fix the first one, you can fix the first one. There is no need to rotate the front carbon, chlorine, hydrogen, no need to rotate. Now look at here. I am going to rotate this part, this, look at this part. Clear?
Yeah.
This one.
Just gonna rotate it over.
And I want to keep hydrogen at this position. So if
Right.
hydrogen is going to at this position, it means methyl should be here and ethyl should be in place of H. Clear? So it should be
Mhm.
ethyl, it should be methyl, and it should be hydrogen. Makes sense?
Okay.
And now
Everything
you can see
rotated.
my chlorine and hydrogen is in the anti side. So we have a double bond. Now look at the groups. Hydrogen and ethyl is anti. So if this is hydrogen, it would be my ethyl. Then tertiary alkyl group and methyl is anti. So if this is my tertiary alkyl, so this is my methyl. Makes sense?
Yes.
So this would be my alkene, and this reaction is called stereospecific. Clear?
Yes.
May I move?
Yes.
Prediction between E1 and E2. So whenever we have 1 degree alkyl and 2 degree alkyl, it gives E2 only. And whenever we have 3 degree alkyl and allylic and benzylic, that gives you E1 and E2. E1 and E2 both. And that depend on the condition, okay?
Okay.
Makes sense?
Mhm.
Now we are going to deal with the prediction of SN1, SN2, E1 and E2. And this is very, very important concept. Clear? So I am
Yes.
going to generate a category. So the very first category is a strong base and weak nucleophile. Strong base and weak nucleophile. The second category is strong base and strong nucleophile. The third category is weak base and strong nucleophile. And the last category is weak base and weak nucleophile. Clear?
Yes.
So I would like to teach you a technique as well at the same time, like how you can figure out easily which one will exist in this category. So strong base and weak nucleophile is generally the bulky one. If you have any bulky attacking species, bulky means like tertiary butoxide,
Butoxide.
yeah, like this tertiary butoxide, DBU, DBN. These are the most common one, okay? So this is called strong base and weak nucleophile. Clear?
Yes.
Now the next one is strong base and strong nucleophile. And this is generally oxygen negative. Oxygen negative is like OH minus, MEO minus, ETO minus. Clear? But do not consider this oxygen minus because this is bulky one, okay? So
Okay.
OH, methoxide, ethoxide. Clear?
Yes.
Next is weak base and strong nucleophile. All the halogens like IBr, iodine, Br minus, Cl minus, and then sulfur one, Rs minus, SH minus, RSH, and H2S. So how can you memorize this one? Sulfur and halogen. Which one? Sulfur and halogen is a strong nucleophile but weak base. Clear?
Yes.
So I can say here in general, halogen, and sulfur. You can see sulfur sounds like S. S is a strong nucleophile, clear?
Yes.
And weak base. Now, weak base and weak nucleophile, this is quite simple. The lone pair one, neutral one, like H2O,
Mm-hmm.
like MeOH, methyl alcohol, and ethyl alcohol. Clear? So these are the most common reagent I'm telling you here.
Okay.
So again, let me explain this. The very first category is bulky. So all the bulky is generally strong base and weak nucleophile. Clear?
Yes.
Alkoxide and hydroxide. This is called alkoxide. Like methoxide, ethoxide, and hydroxide. They are strong base as well as a strong nucleophile. Clear?
Mm-hmm.
All the halogen and sulfur. This is a strong nucleophile but weak base. And neutral one like alcohol and water, that is weak base and weak nucleophile. Clear?
Yes.
Now the second category. Here I am going to tell you strong base, weak nucleophile, the strong base and strong nucleophile, weak base and strong nucleophile, weak base and weak nucleophile. Clear?
Mm-hmm.
And here I am going to write down the substrate like 1 degree, 2 degree, and this is 3 degree. Clear?
Yes.
So look at here, strong base, strong base. In the first case, look at the first column, strong base, weak nucleophile. Base is strong. It means whenever base is strong, it means elimination favored. Am I right?
Yes.
And whenever you have 1 degree, 2 degree, or 3 degree, any degree of alkyl halide, it would always be E2, E2, E2. Any doubt about the first category?
No.
Whenever base is strong, and how can you say which one is my strong base? Negative charge one, okay? In general, we have done already the category of strong base, weak nucleophile, weak base, strong nucleophile. Clear? So
Yes.
this is only E2. Now look at the second one. Strong base as well as strong nucleophile. You know that whenever tertiary alkyl you have, it means branching. Clear? This is called branching.
Yeah.
And substitution is not going to good for strong nucleophile means SN2. Clear?
Mm-hmm.
So
Mm-hmm.
you know that for tertiary SN2 is not favorable. Am I right?
Mm-hmm.
So it would be E2 again. Clear?
Got it.
And here E2 again favorable than SN2. And here SN2 is more than E2. Means in case of primary halide, because there is no steric crowding here, there is no steric crowding, so you can say substitution dominates over elimination. But whenever branching starts, you can see secondary have branching like this. You can see at this one. So in this case, nucleophilic substitution is not favorable, so we can say elimination would be good. Clear? Makes sense?
Mm-hmm.
So simply,
Yes.
whenever anything is strong, either strong base is weak nucleophile or strong base is strong nucleophile. So in terms of strong base and strong nucleophile, only the primary, except primary, the secondary, tertiary is only E2, 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 E2. Clear?
Mm-hmm.
But whenever you have primary, then SN2. Clear?
Got it.
Now the next one is a weak base and strong nucleophile. Now it's simple. Here nucleophilic part is dominant over basic character. So whenever nucleophilic part is dominant over basic character, it means substitution dominates over elimination. Clear? So
Mm-hmm.
you know that 1 degree generally gives SN2, so we can say SN2. 2 degree also gives SN2. Only tertiary can give SN1. Clear?
Yep.
Now the weak base and weak nucleophile is quite simple. The 1 degree cannot give any reaction, 2 degree cannot give any reaction, but in third case, tertiary, the SN1 and E1 is equally favorable, but it depends on the nature of product. If your alkene is tetra or tri-substituted, then alkene dominates, means elimination dominates over substitution. And if your alkene is not tetra, then substitution dominates over elimination. Clear? Like mono or di-substituted. Make sense? So let me tell you some example, then it would help you. Look at the first case. What is the nature of this attacking species? What is this?
That's bulky, right?
Yeah, so bulky means elimination favored. So this is alpha, this is beta. So you have just this one. Clear?
Yes.
Major. And if you want to draw substitution means product, then tertiary butoxide would replace this bromine, and that is not important. Now look at this case. This one is important. Now this H2O is my weak base as well as weak nucleophile. Clear?
Yes.
And this bromide is a tertiary one. So you know that whenever you have tertiary, then SN1 and E1 is equally favorable, but it depends on the nature of alkene. If you want to draw your alkene, then you know that this is alpha, this is beta. This one is also beta, this one is also beta. Am I right? So you have 3D beta, beta 1, beta 2, beta 3. Make sense?
Yep.
But beta 1 and beta 2 is same. So we can say beta 1 only. And this is beta 2. Clear? So the number of product would be here only 2. So it should be either this one, this one. Clear? These two product could form. Clear?
Yes.
And this is tetra substituted. This is tri substitute. Yeah, this is di sub. Means we will see only this one because this is Sergev one. So we can say this one. In alkene, this one is a major. And if you want to draw your substitution product, then it would be this. And I told you that whenever alkene is tetra substituted, then that elimination would be the major. Means this would be the major, the substitution product would be minor. Clear?
Yes.
If you have just mono substituted alkene as a major, then we will go with substitution product. Clear?
Makes sense.
Okay, I told you already, whenever methoxide, hydroxide, and ethoxide, this is ethoxide, then it is a strong base as well as a strong nucleophile. Clear? And you know that this is secondary halide. So secondary halide in nucleophilic substitution gives SN2 product, not SN1. So if you want to draw substitution, then it would be dash OET. Why dash? Because this is a chiral one and SN2 have inversion. So which would be dash? Clear?
Yes.
And if you want to draw elimination product, then you have this elimination, the trans alkene would be the major one. Clear? Trans alkene. Now the important thing is which one would be major here, substitution product or elimination product? Look at the table. Whenever strong base and strong nucleophile, if there is a branching, you can see secondary have some branching. So substitution is not good. We will go with E2. So this one would be the major. Clear?
Yes.
If there is no branching here like primary, then we can say SN2. Clear? Let's do some exercise. So here problem 1, we have to find out the nature of reaction SN1, SN2, E1 and E2. Clear?
Just
Look at the first reaction. Wait. NaOH. This is NaOH. So look at how we can identify the nature of reaction. So first of
mhm.
all, this is tertiary halide. The second thing, the nature of reagent is strong base and what? Strong
Weak,
base and NaOH is
uh,
what? NaOH is what? Is strong base and strong
strong
nucleophile.
nuclear. Strong, yeah, because it has
Yes.
lone pairs, right? Or no?
Yes. Negative
Okay.
charge. Negative charge.
Negative charge. Yeah, yeah, sorry.
So this is a strong base and a strong nucleophile. So you know that if it is behaving as a nucleophile, then it would give SN2. And if it is a strong base, then you have E2. So you know that this is branching here. This is branching, tertiary. So SN2 is not favorable, only E2. Clear?
Yes.
So if you want to draw the E2 product, then multiple products you have. Like one, the double bond should be here. One, the double bond should be either top or right. Clear?
Mm-hmm.
And out of them, this one would be the major because Sergev. Clear?
Yep. Got it.
So overall, we can say it would give E2 reaction. Make sense?
Mm-hmm.
Any doubt about this?
No.
Now look at this one. Okay, what is the nature of this alkyl halide?
Tertiary.
Very good. What is the nature of attacking species? Bulky base means
So
a strong
bulky.
base. So a strong base means what? E2.
E2, yeah.
So you have multiple product again, but this is the major because more substituted. There is another alkene, this would be clear, but we will select this one as a major. Why? Because we have Sedjaf alkene, more substituted. Makes sense? More alpha H. So overall, we can say it would give E2 reaction. Clear?
Got it.
Any doubt?
No. Um, actually, let me see.
Tell me what is happening.
Um, I'm like trying to remember the Zaitsev and Hoffman. And
Yes,
when you said Hoffman,
Sedjaf is the more alpha H and Halfman is a less alpha H.
so, but didn't we use like, isn't that a bulky base? So wouldn't Hoffman be major?
Oh, yes, yes,
Right?
yes, you're right. Absolutely.
Okay, that's what I was
Good
confused.
job.
Okay.
This is major, this is minor. Well done. Clear?
Mm-hmm. Yeah.
So here Halfman would be major because we are using a bulky base. Clear? Now
Mm-hmm.
next is NaSH. Let me know the nature of SH minus. What is this? So this is a strong
Uh,
nucleophile and weak base. Clear?
yes.
So if nucleophilic character is strong, it means the reaction would be SN2. And if the reaction is SN2, it means iodine is substituted by SH. Clear?
Mm-hmm.
It would be SN2. Make sense?
Got it. So usually when it's a strong nucleophile,
Yeah,
like it's usually substitution, but
yeah.
when it's a strong
Like
base, it's
this.
usually
Suppose I am
elimination.
saying strong nucleophile but weak base. So we will say
Mm-hmm.
substitution dominates. If I am saying strong base and weak nucleophile, then we will say elimination dominates. Clear? Like this.
Right. Got it.
But whenever you have a strong nucleophile and a strong base, then it depends on the nature of alkyl halide. Like if you have a branching, then elimination. If it is primary, then elimination. Clear?
Yes. Got
Substitution.
it.
If it is primary, then SN2, and if it is branching, then E2. Clear?
Yep.
So like this one, we are using NaOH. So NaOH is my strong base as well as strong nucleophile. Clear? And this
Mm-hmm.
is primary. There is no branching. So we can say SN2 dominates over E2. So if SN2 dominates, so it means the Br is going to substitute by OH. So this is SN2 product. Clear?
Mm-hmm.
Any doubt?
No.
But if you are going to take this one as example, and we are using NaOMe. So NaOMe is what? Again, is strong base, is strong nucleophile.
Mm-hmm.
But there is a branching. Can you see?
Yeah.
So no substitution, only elimination.
Elimination. Yeah.
And this time more substituted would be the major one. Clear?
Yes.
So this one would be the major. And in more substituted, if it is showing cis trans, then you should draw the trans one. Okay?
Yes.
Make sense?
Mm-hmm.
Any doubt?
No.
All done?
Yes.
So this is all about SN1, SN2, E1 and E2. Okay? Any doubt?
Mm-mm.
Perfect. So we have done this chapter. In the next sitting, we will start arrow pushing, okay?
Okay.
Or addition reactions of alkene, or we can start the chapter alkene. We will decide, like, I think arrow pushing is more important than alkene, so we will go with arrow pushing, okay?
Okay.
Perfect. And you can try the questions based on SN1, SN2, E1 and E2. Clear?
Got it. I'll do that.
Thank you so much. Bye.
Bye.